In this lecture, we are going to solve the next problem on a steady state error. So the problem that we are having here is having a unity feedback system, and the transfer function is given in the form of g of s, and it is asked to determine the type of the system, all error coefficients, and we need to determine the steady state error for input. This input consists of step input, ramp input, as well as parabolic input. So we'll see how to solve this kind of a problem. So first step will be to write this in a normal form. So we know that the transfer function is written as g of s into h of s. So since h of s is unity, we are not having that term here. The transfer function will be 10 s plus 2 s plus 3 divided by s, s plus 1, s plus 5, and s plus 4. So the first step will be to convert this into time constant form. So it will be g of s into h of s, and it will be equal to 10 into 2 into 3, because we have to take out 2 from this term and 3 from this term. So because of that, we are having 2 into 3 here. So first bracket will be written as 1 plus s by 2, and second bracket will be written as 1 plus s by 3 divided by, we will be having 5 into 4 into s. So first bracket we will be having as it is, because the constant that we are having inside it is 1. Now next bracket we will be having as 1 plus s by 5, and last bracket we will be having as 1 plus s by 4. So because of this 5 and 4, we are having 5 and 4 out here. So now what we can do, we can simplify this a constant. This will be 5 4s are 20, and we will be having 2 into 10, so that is 20. So we can cancel this 10 into 2 and 4 into 5, and we will be having the transfer function as 3 1 plus s by 2 1 plus s by 3 divided by s into 1 plus s 1 plus s by 5 1 plus s by 4. So now based on this transfer function, we can directly comment on the type of system. So here we are having one separate s. So we know the power of this s is 1. So we can say that j is equal to 1 here. So this indicates that it is a type 1 system. Next we have to calculate error coefficient. So first we'll calculate Kp, that is positional error coefficient, and it is given by limit s tends to 0 g of s into h of s. So let's substitute the value of transfer function here. Limit s tends to 0, we are having 3 in bracket 1 plus s by 2 1 plus s by 3 divided by s into 1 plus s 1 plus s by 5 1 plus s by 4. Now when we are going to take limit s tends to 0, so all the bracket will contribute 1, but because of this s in the denominator, which will going to be 0, so this Kp value will become 3 by 0, and that is infinity. Now we can find next error coefficient, that is Kv. So it is given by limit s tends to 0 s into g of s into h of s. So it will be limit s tends to 0 s into the transfer function. So it is 3 into 1 plus s by 2 1 plus s by 3 divided by s into 1 plus s 1 plus s by 5, and then 1 plus s by 4. Now here in numerator and denominator we are having separate s, so both we can cancel. So we will be left with s tends to 0 and this entire transfer function. Now when we take limit s tends to 0, so all the bracket in numerator and denominator will going to give us 1, because 1 being constant will be kept as it is, and other value will become 0 because of s. So after taking a limit, we will be having here value as 3. Next we have to determine Ka, that is acceleration error coefficient. Formula for that we are having as limit s tends to 0 s square g of s into h of s. So when we substitute transfer function value, we will be having here limit s tends to 0 s square into 3 1 plus s by 2 1 plus s by 3 divided by s into 1 plus s, 1 plus s by 5, 1 plus s by 4. So now here from numerator and denominator we can cancel 1s. So after cancelling s, when we take the limit s tends to 0, so because of this separate s which is remaining here in the numerator, we will be having this entire value to be 0. So Ka we are going to get as 0. Now once we got all the error coefficient, we can determine the steady state error for this given input. So let's find that. So input that we are having here is u of t is equal to 3 plus t square. Now we can take Laplace here so that we can have the inputs in our favorable form. So by taking Laplace, this value will become u of s, and here we will be having 3 by s plus this t will become 1 by s square plus this will become 2 by s cube. So now from this expression we can make out that input is a contribution of step input of magnitude 3, ramp input of magnitude 1, and parabolic input of magnitude 2. So now here, in order to find the steady state error, what we'll do, we'll first find the steady state error because of this input, that is a step input. Then we are going to determine steady state error because of ramp input, and after that we are going to find the steady state error because of the parabolic input, and later on by using the superposition principle we can add them to get the overall steady state error for this transfer function based on this given input. So let's do that. First we'll find steady state error for step input of magnitude 3. So we know that steady state error for a step input is given by a by 1 plus kp. So a, that is the magnitude of input, we got here as 3 divided by 1 plus we got kp as infinity. So 1 plus infinity is infinity and 3 divided by infinity will be 0. So we got steady state error as 0 when we are considering the step part of this input. Next, we need to find steady state error for ramp input of magnitude 1. So steady state error is given by a by kv. So a, that is the magnitude, we got here as 1 divided by kv we got as 3. So based on the ramp input contribution of this input, we got steady state error as constant, that is 1 by 3. Now let's find for the next one, that is steady state error for parabolic input of magnitude 2 here. So the error will be given by a by ka. So a we got here as 2 divided by we got ka as 0. So this value will be infinity. So the parabolic part of this input is giving us the steady state error for this system as infinity. Now once we got the steady state error for the respective input, we can use the superposition theorem to add these steady state errors to get the overall steady state error of the system. So let's write the steady state error here, the total overall steady state error for the system. So it will be E of SS is equal to the steady state error contribution because of the step input, that is 0, plus the steady state error contribution of ramp input is 1 by 3, plus the steady state error contribution of parabolic input that we got as infinity. So when we add these three terms, it will be infinity, because if you add anything to infinity, it will be always infinity. So based on this steady state error, we can say that when we are using the given input, the steady state error of the system will be infinity. So whenever we are having input which is a contribution of various standard input, we can solve in this way by determining individual steady state error contribution, and later on we can use the superposition theorem to add all of them to get the overall steady state error. So now with this we'll end here.